It's a great pleasure to be able to speak at this nice conference. Let me first say that this video is pre-recorded because of the time zone difference between Japan and Brazil. Right now, my small children are asleep, not very far from me, so I don't want to make any noise and wake them up. That would cause a lot of trouble for me. That said, I'm still on the other side of the Zoom, so you can ask me questions afterwards, but I'm going to answer you very quietly. So let me start with a kind of introduction. String theorists often say that string theory is miraculously free of inconsistency, and when they feel particularly arrogant, we sometimes say, well, string theory is or seems to be the only consistent theory of quantum gravity. My main question today is whether we are really sure about the consistency. Are we really sure about that? For example, let's consider Witten's SU2 anomaly. In fourth dimensions, as you know, there is a non-trivial large gauge transformation associated to pi 4 of SU2, which happens to be Z2. So if you have n doublet Weyl fermions, then you can perform this discrete gauge transformation, and that produces a phase which is minus 1 to the power n. So the theory is inconsistent if the number n of doublet Weyl fermions is odd. Let us now ask the following question. Is Witten's SU2 anomaly absent in 4D heterotic compactifications? Well, somewhat surprisingly, this rather fundamental question is still open in 2021. I learned this question from my colleagues in IPMU during the tea time slightly before the pandemic. They studied this question assuming that there are four-dimensional n equals 2 supersymmetry. And they showed that the anomaly vanishes in many cases, but they didn't find a universal proof either. So their analysis was presented in a paper here, Enoki Sato Watari, from May last year. Today, I'm not going to discuss this Witten's anomaly due to technical reasons. Instead, I'm going to discuss a related but slightly different global anomaly, which is a Z24 global anomaly in 2D heterotic compactifications. And the aim of this talk is to show that it vanishes. For this purpose, I'm going to use the mathematical theory of topological modular forms and the associated Segal-Stolz-Teichner conjecture. So let me start. Let's first remind ourselves the perturbative heterotic strings construction. So let's consider heterotic compactification to spacetime dimensions d. The worldsheet theory of the string consists of the following. Of course, you have superghosts, which contributes minus 26 to CL and minus 15 to CR. Next, you have bosons for the uncompactified spacetime. They are fermionic partners. Together, they contribute d to left moving central charge and 3/2 d to the right moving central charge. Therefore, in order to balance, you need to have an internal CFT, which has CL equal to 296 minus d and CR given by 15 minus 3/2 d. In particular, let's consider the case when d equals 10. So that's the prototypical case. The internal CFT should have the well-known value of CL being 16, and CR needs to vanish. As you know, there are only two possible choices. One is SL32, current algebra. The other is E8 times E8. In both cases, the perturbative anomaly miraculously cancels, as was first shown by Green and Schwartz, 1984. It then follows that the perturbative anomaly automatically cancels for arbitrarily smooth geometric compactifications, just because it vanishes in 10 dimensions. But the good thing about heterotic string is that you can use a genuine CFT which might not come from any geometry as an internal CFT, as long as it has the correct central charge. Luckily, it is known that perturbative anomaly always cancels, independent of whether the internal CFT is semi-classical or not. So that was done by Lerche, Nielsen, Skelekens, and Warner in 1988. So the question of the vanishing of the perturbative anomaly is settled. What about the global anomalies? Well, in 10D E8 times E8 superstring, well, it was shown to vanish in Witten's paper in 1986. This implies again that the global anomaly automatically vanishes in all smooth geometric compactifications of E8 times E8 heterotic strings. But again, there can be non-geometric compactifications where the internal CFT does not come from classical geometry. So, let me talk about the particular two-dimensional anomaly I'm going to discuss. It's a bit complicated, confusing, because the worldsheet is 2D and the resulting spacetime theory is also 2D. The internal CFT, in this case, has to have this particular central charge at 24, 12, and we need to count how many massless fermions there are. For this purpose, well, you need to open the textbook on perturbative string theory, and you find the following. Massless fermions in the spacetime theory comes from R-sector vacuum states of the internal CFT, and then the spacetime chirality is basically given by the right-moving fermion number of the internal CFT. Therefore, basically, the elliptic genus of the internal CFT encodes the net chiral number of fermions. So it gives the fermion anomaly. So let's say the elliptic genus of the internal CFT is given by this expression. So elliptic genus is the trace over the R-sector Hilbert space with an insertion of -1 to the right-moving fermion number. So this projects out the right-moving modes to its zero energy states, and you have a contribution from the left movers, which are non-supersymmetric. Because the left-moving central charge is 24, this series starts from the term of the order Q inverse. So let's say it's given by AQ inverse plus B plus ... Then the standard technique shows that the leading coefficient A is the net chiral number of two-dimensional spacetime gravitino, and B is the net chiral number of the spacetime spin 1/2 fermion. Therefore, the total fermion anomaly polynomial can be easily computed because the contribution from a gravitino or contribution from a fermion is known, and it's given by this, -24A plus B times P1 over 48, where P1 is the Pontryagin class, which is basically trace R squared. So a gravitino contributes a 24 times that of a fermion. That's not the only contribution to the anomaly. You need to think about the B-field one-point function too. So string one-loop perturbation theory automatically generates the B-field one-point function of this form, and the coefficient n can be found by string perturbation theory, which boils down to the integral over the fundamental region of the SL2Z of the elliptic genus of the internal CFT, and it results in basically -A plus B over 24, as was found in 95 and 96. The reason why this coupling to B produces the anomaly is that the gauge invariant field strength of B, which is H, is not just dB, but has a contribution coming from the Chern-Simons term of the gravitational connection, spin connection. Therefore, integral of B has the same anomalous variation as would come from the anomaly polynomial P1 over 2. Summarizing, let's say that elliptic genus of the internal CFT is AQ inverse plus B plus ... Then this controls both the fermion anomaly and the B-field one-point coupling. So the fermion anomaly is -24A plus B times -P1 over 48, while the B-field coupling is this, -A plus B over 24 and the integral of B. As I said, the integral of B has the same anomalous variation as P1 over 2, So you can see that these two contributions nicely cancel out, and the perturbative anomaly vanishes. This is that Green-Schwarz mechanism in 2D. But that's not the end of the story. The B-field coupling still poses a problem when b over 24 is not an integer, because the integral over b transforms non-trivially under the large gauge transformation of b. So this part can shift by 1. So if b over 24 is not an integer, this coupling can produce a non-trivial phase, which is 24th roots of unity. So when b is not divisible by 24, this particular system can have a Z24 valued global anomaly. So that's the global anomaly I'd like to discuss today. Let's summarize. The central question is now formulated as follows. So let's take an n equals 0, 1 two-dimensional SCFT with CL and CR given by 24 and 12. So that's the right structure for 2D theory to be used as an internal CFT for heterotic compactification down to 2D. Let's say its elliptic genus is given by AQ inverse plus B plus dot dot dot. The main question is whether the coefficient B, constant term B, is always divisible by 24. So this is not a string theory or quantum gravity question anymore. It's just a 2D CFT question, and it's quite a peculiar one. I've never thought about the divisibility of the constant part of the elliptic genus before I thought about this question. And I don't know how to approach this question in the standard way. One thing you can do is to go over the list of known examples, and if you go over various papers in the past, you can find many examples, and you find that B is always divisible by 24. But can we show this in general? Let's first use the theory of modular forms. So let's discuss the elliptic genus again. So given a theory T, its elliptic genus is the Hilbert space, torus over the Hilbert space in the R sector with the -1 to the right moving Fermi number, and you count the number of states in the left moving non-supersymmetric side. So that's the partition function of the theory on T2 with the periodic spin structure, which makes it almost modular invariant, but up to subtle phases given by 24th roots of unity, which comes from the worldsheet gravitational anomaly, which is given by the difference between CR and CL. So that makes the analysis a bit complicated. So it helps us to cancel this anomaly by adding new left-moving fermions, where nu is given by twice CR minus CL, so that the combined system doesn't have any global anomaly, gravitational worldsheet anomaly. What we have is then this combination. So you have the original elliptic genus, and you multiply that by a fermionic contribution, which is given by the nth power of the Dedekind eta. We now have the following transformation law for this combined object. So if you perform SL2Z transformation, you get this prefactor. This makes this combination phi w into a modular form of weight nu over 2. Mathematicians call phi w the Witten genus of this theory. So let's come back to our original question of heterotic compactifications to 2D. In this case, nu is given by -24, which means that we need to consider eta to the power -24 times the elliptic genus, which has this form. Combined, this is the modular form of weight -12 with integer coefficients, because they count the number of states, and it can have poles of order at most 2. So this part, eta to -24, can have pole of order 1, and you also have Q inverse. So using the standard elementary theory of modular forms, you find the following. Phi w, in our case, needs to be an integral linear combination of two possibilities. One is e4 to the cube divided by delta squared, where e4 is the Eisenstein series normalized so that it has integer expansion coefficients, and delta is the modular discriminant, which is eta to the power 24. So that's the first possibility, and the second possibility is just the inverse of delta. So the theory of modular forms allow us to determine the entire elliptic genus in terms of A and B, so that's a progress, but it doesn't tell whether B is divisible by 24. For that purpose, you need to use a more sophisticated theory. That's the theory of topological modular forms. So what is this? Well, the ring of topological modular forms generalizes and refines the ring of ordinary modular forms. So it was mathematically constructed by Hopkins and collaborators around 2000 using an amalgam of algebraic topology and algebraic geometry. And this topological modular forms is useful for us thanks to the Segal-Stolz-Teichner conjecture, which says the following. So TMF nu is an abelian group constructed by mathematician, but that seems to be conjecturally equal to the following. So you consider the space of two-dimensional n equals 0, 1 supersymmetric theories with a specified amount of nu, which is the difference between the left-moving and right-moving central charge, and you classify them according to continuous deformations like irrelevant, relevant marginal deformations, or RG flows, or adding some SUSY breaking sector. In particular, if we are given a n equals 0, 1 SCFT T in 2 dimensions with a specified nu, that should determine a class T in this abelian group TMF nu. So why is this conjecture plausible? Well, mathematicians, when they constructed TMF, constructed also a map phi w, which is a map from TMF nu to the set of modular forms of weight nu over 2 with integer coefficients and poles, which for us should correspond to sending a theory, two-dimensional theory T, to its Witten genus, which is an elliptic genus multiplied by Dedekind eta. Mathematicians also know how to describe sigma models in terms of TMF class. So given a new dimensional manifold together with B field satisfying certain conditions, we should be able to describe two-dimensional sigma model with M as the target space together with a B field, and that should determine some 0, 1 SCFT in 2D. So in view of the conjecture, it should determine a class in TMF nu, and let's denote that as sigma, mu, and B. Mathematicians also showed that when they combined these two constructions of getting a TMF class and then mapping to the modular form, and then they get some modular forms, but that turns out to be equal to what we expect as a physicist. So in that case, sigma model, we know the sigma model, so we can compute the elliptic genus of that sigma model, and we can multiply that with the Dedekind eta, and that agrees with what mathematicians constructed. So that gives a partial justification for this conjecture. The good thing about mathematicians' work is that they determined the image of this map phi w completely. So for example, delta, which was modular discriminant to some power k, is in the image of phi w if and only if the coefficient d is a multiple of 24 over GCD 24 comma k. So that's a weird statement, and let's use that. So our question was the following. We take 2D n equals 0, 1 SCFT with the central charge 24, 12, and let's say its elliptic genus is A Q inverse plus B plus dot dot dot. The question was whether the constant term B was divisible by 24. Please recall that otherwise heterotic compactifications to 2D can have a Z24 global anomaly. We already argued, just by using the ordinary theory of modular forms, that the written genus of this theory is a linear combination of either this one or the other one. But the added information we now have is that, assuming the conjecture and the mathematical result, the image of phi w contains only d delta k, where d is a multiple of 24 over GCD 24, k. In our case, k is minus 1, right? So 24 divided by GCD 24, 1 minus 1 is 24. This means that the coefficient minus 744 times 8 plus b should also be divisible by 24, meaning that b itself is divisible by 24. That's what you want to show. Done. Great. But you would ask me, usually you started your talk by talking about Witten's SU2 anomaly. What happened to that? Well, more generally, the question of global anomaly of heterotic compactifications down to d dimensions with gauge symmetry G can be translated to the study of a certain TMF group. So that's a question in algebraic topology. That is a very difficult groups to compute, and I asked a number of friends of mine who are mathematicians, but nobody computed it for me. But one mathematician told me the following: well, there's a way to show that the global anomaly vanishes without doing any case-by-case analysis. The important point is to consider all cases at once and use the structural result of TMF. So that's a work in progress with Yamashita, brilliant young mathematician in Kyoto, and I hope to report it in a preprint soon. Let me finish with some comments. Clearly, we are not really done, right? We simply transferred the question of the global anomalies of heterotic strings to the validity of the Segal-Stolz-Teichner conjecture, right? So it's important, I think, to test the conjecture in our own way. Well, there are a couple of works doing exactly that, like this. And let me just add one implication of the conjecture so that you can think about it. So as I said, the image of this map, phi w, has been mathematically determined. And in particular, delta to the power k is in the image of phi w only if and only if d is a multiple of 24 over GCD 24, k. So what does it mean? Well, it may mean many things, but one consequence in our language is as follows. So if the elliptic genus of two-dimensional 0, 1 theory is simply 1, then the difference of the central charge, CL minus CR, is divisible by 288. Conversely, there should be a two-dimensional n equal 0, 1 theory whose elliptic genus is just 1 without any dependence on Q, and CL minus CR is plus minus 288. So that particular theory will be quite a marvelous one, but as far as I know, nobody has constructed it. Okay, let me summarize. Today I considered global anomalies in heterotic string theories. Such questions can be answered using the mathematical theory of TMF, using the Segal-Stolz-Teichner conjecture, saying that TMF nu describes the classification result of n equals 0, 1 supersymmetric theory with specified difference of the left-moving and right-moving central charge up to continuous deformation. And this conjecture not only tells us about heterotic anomalies, but also many unexplored properties of two-dimensional theories, which I think are worth pursuing. And I just want to say that the list of HEP-TH papers on TMF is not very long. The exhaustive list is really this. So there are less than 10 papers. It's a young field, and I would welcome any newcomers to the field. Thank you very much.